Hi everyone, I'll present our paper with the title All Models Are Wrong, Some Are Useful, Model Selection with Limited Labels, that recently got accepted at AI Stats, and this is a collaboration with TU Delft. So starting from the motivation, the size of pre-trained models is growing. Here I've listed some of the papers that have started that trend that are quite popular. And all of these models are more or less available on platforms such as Hugging Face, PyTorch, and TensorFlow Hub, so a user can just download it, the pre-trained weights, and start using it. But the question that rises is how to select the best pre-trained model. So as time went, the size of the dataset has been growing. What is the problem? The problem is that it's not anymore efficient to evaluate on all data points. Another problem is that many of the points and the datasets are actually unlabeled. So you have some cost you need to pay for labeling the dataset. And saying that, active model selection was born. So these are some of the papers that actually started this trend. So what is active model selection? That is model validation using a small but informative labeled subset to assess the performance and predict it on the entire dataset. The assumptions that were made in previous works are that there is a fixed number of available models that we are trying to estimate how they will perform on that subset. Another assumption is that this is restricted to specific model families, for example, Gaussian processes or some specific neural network architectures. And in this work, we asked the question, how can we efficiently select the most informative examples for labeling to choose the best classifier in a model agnostic way? So the contribution in this paper is that we introduce model selector. So model selector is a fully model agnostic approach for identifying the best pre-trained model, but using a limited number of label examples. So unlike the existing methods whose assumptions we mentioned previously. And I'm here showing just a preview of some of the results that we'll talk about later. So model selector, as said, is fully model agnostic, makes no assumptions on the underlying models, and it relies solely on hard predictions. So when I say hard predictions, I mean that from a model, you do not get an output. Like if you've got some classes, what would be the probability of each class? You just get the output that this model predicts for a data point to be class A, B, C, D. Now, why is this important in practice? Is because usually nowadays APIs do not give you the soft predictions. Why? Because with that, you could actually distill their underlying model from their and get their data. So they don't want to do that, and they just give you the hard predictions. So in the paper, we actually conducted extensive experiments, and we compared our method against a range of adapted methods over 1,500 models across 18 different model collections and 16 different datasets. So the framework we propose in the paper is the following. We start with n unlabeled examples, some data points. It can be, for example, Glue, Benchmark, ImageNet, or whatever. Then we input that into our M pre-trained models that we download from Hugging Face, PyTorch Hub, and TensorFlow Hub. Each model classifies each data point examples, so you end up with n times m model predictions. And then this goes into the model selector. In the model selector, we iteratively query the oracle and get the label and repeat this process until we exhaust our budget B. We end up with B-labeled examples, and then we evaluate the models on only these B-labeled examples to find the model winner, and the output is the best model for inference on the remaining n-b examples, where this n-b is much larger than the budget B. Okay, so now explaining the model selector. Given that accuracy is our chosen utility measure, what we focus on is the binary outcome of the correct versus incorrect predictions made by a model H on these labeled examples. So with this attention, we introduce the following equation, where this epsilon represents the probability of this binary outcome. So this setting actually aligns closely with the setting from the paper Chen listed here. So here, H star represents actually the true underlying best model, and capital H is actually a random variable that represents our unknown model that we suspect to be. So since you're using just a single parameter for the error probability, this is a major simplification of the problem introduced in the Chen paper. So given that we have an unlabeled data pool D, we want to identify the most informative examples for model selection. And we characterize the information in the labels using Shannon's mutual information. So our objective can be formalized as the equation shown here on the slide, and that is finding the argmax of mutual information between H and the label L with the budget B. So the strategy of the model selector is to greedily pick the unlabeled example at iteration t that will provide the maximal information gain. We just write it as this. And here UT represents unlabeled data, LT represents the labeled data. And now, in order to compute this information gain, we write the previous equation as in terms of differential entropies shown here on the slides. Now, this expectation or y is taken since the true y is actually unknown. We have to use like a uniform probability over all the possible classes. What can be shown is that the first equation here is actually equivalent to minimizing the model posterior uncertainty. And this is shown in the paper cited below. Okay, continuing from that, what we actually are calculating is something we call hypothetical model posterior, which is proportional to the equation shown here. So, and we get this by just applying the Bayes rule and obtain this. So why do we call it hypothetical? Is because we just do the calculation over all possible classes. For example, in Cypher 10, that will be just calculating this over classes 1 to 10. So now, if we assume that we've got a uniform distribution over all models, which is reasonable, since we do not want to make assumptions on the underlying models, our hypothetical model posterior becomes this. So here, notice that we are using epsilon that we defined at the beginning, which is the error probability. And here, H represents the number of correct predictions of classifiers. So we are actually keeping track of how many times there was a correct prediction for each of the classifiers and how many times did they make a mistake. So what happens at iteration t is that model selector selects the most informative xt and queries Oracle for yt, and then performs the updates, that is, adds another point to a labeled dataset and removes it from the unlabeled dataset and updates the hypothetical model posterior. So the full details and the pseudocode can be found in the paper. All of this repeats up to budget B. So I haven't mentioned how do we actually select the parameter epsilon, how do we determine it? And we do a grid search over a range of values such that we find an epsilon that yields the best performance in terms of accurately identifying the best model. However, this is done without actually requiring the labels. So what we start is we start this procedure by assigning noisy labels to data points. What is a noisy label is you just take your from the framework those n times m predictions and you just do majority vote for each data point. So first, we do a coarse-grained search with larger steps, and we want to find like a promising interval for epsilon. So we do 0.25 to 0.5 in steps of 0.05. And after we found that, we then do a fine-grained search within these intervals. So what is nice about this is because it's efficient, it can actually reuse the label predictions that were previously calculated. Now, this epsilon parameter can actually be interpreted in terms of model disagreement within the exploration-exploitation trade-off, meaning that if your epsilon is closer to 0.5, it will be more likely to act as just random sampling. Now, all of this we evaluate on both vision tasks and NLP tasks. So just to highlight some things, we use 3 different model collections for ImageNet. We use 2 different model collections of various model architectures and accuracies from Cypher10. We use PAX dataset. So in vision tasks, we evaluate on going from 6 classes to 1,000 different classes. We use networks such as ResNets, EfficientNets, MobileNets, and we evaluate it even on a challenging domain adaptation setting, where in the test set you actually get a distribution shift. Regarding the NLP tasks, we evaluated this on the GLUE benchmark. And in the GLUE benchmark, it goes from just having 71 examples in the test set to actually having 40,000 data points. And the number of classes that we are predicting here is going from binary classification to 3 classes. The models we download from Hugging Face are some of which are BERT, DistillBERT, Roberta, GPT models, and so on. All of this results in a total of 18 model collections on 16 different data sets with over 1.5K pre-trained models. So to give you a sense of all of the variety that we are trying to see when taking all of these different models, I'm showing the probability distributions of the accuracy for each of the model collection and the data set. To highlight, so you can see, for example, for Cypher10, we're using the same data set, but we're trying out model collections with lower accuracy from 40 to 60 and from 60 to 80 accuracy. So models that we choose, for example, for Cypher10 have uniform model accuracy. There is the same amount of equally good and equally bad models. We are also testing a situation, for example, on the Cola dataset where most of the models are equally good and there is a very small proportion of bad models. We are testing also a scenario on WNLI where there are noisy models that have accuracy just 5%. So we are testing on a wide range of possible model accuracy without making any assumptions about their distributions. So since we are actually the first to work in this scenario, we propose some of the baselines. The first baseline is the random, the most simplest baseline here. The second one is the uncertainty sampling that we adapted, and it creates a probability distribution over classes based on the predictions from all of the models and then ranks them by their entropy and selects the top B examples with the highest entropy. The second uncertainty sampling method is margin sampling, which is also non-adaptive, and selects examples with the smallest margin, defined as the difference between the highest and the second highest class probability. Now we adopted two methods from the literature, that is active model comparison and variance minimization approach. Although they are not for our setting, because active model comparison was actually just comparing two models, and variance minimization approach requires soft predictions, we managed to modify them and use them in our setting. Now, going to the evaluation protocol that we use in the paper, is we start with entire test set. And now what we do is we uniformly sample NIID instances and create something that we call realizations. So realization 1 is a subset of the entire test set, realization 2 is a subset of the entire test set, and then realization I is also a subset. And on all of these, we perform the same procedure with the budget B inputted into model selector. We perform these realizations and sampling in order to get some statistical behavior and see that the behavior of model selector is not just an artifact of a random seed, and that the variance is not too high. The performance metrics that we define in the paper are the following. The first is the identification probability. So what is identification probability? That is a fraction of realizations where the method successfully has identified the true best model on that realization. We identify label efficiency, that is the reduction in the number of labels that we need to select a model that is near best, that is in delta vicinity over all realizations. And third is the robustness metric, and that represents we calculate it as the 95th percentile accuracy gap across all realizations. So here we show the results of the best model identification probability across all datasets. So as you can see, we continuously outperform the baseline methods. The best competing method we have seen is uncertainty. And we have seen that model selector even works in challenging scenarios with distribution shift on the drift dataset. So model selector is capable of learning the epsilon parameter in a self-supervised manner from these model predictions, and it automatically detects this distribution shift. So what happens is that model selector actually adjusts epsilon to 0.5, which is actually mimicking random sampling. Because on this dataset, with the distribution shift, random sampling is the best thing to do. So we have also seen that model selector is capable to outperform the baselines on a dataset WNLI that has just 70 examples. So you don't need a lot of examples in the dataset such that will model selector be able to identify the best model. So as far as it goes, model selector is capable of reducing the labeling costs by up to 94%. So next we examine the label efficiency for near best model from a different perspective. So here we evaluated the budget required to select the best or near best model in the delta vicinity. And we did that for delta being 1%, 0.5%, and 0.1%. So this table shows the percentage reduction in the number of labels that are required for model selector to select a near best model compared to the best competing method. So what we can see from here is that we consistently reduce the labeling cost to reach the delta vicinity of the true best model. And we show that it's more label efficient for near best models. Why is this important? Is because in practice, if you've got like different models from Hugging Face and they vary in accuracy just 0.1%, like you've got Bert and Roberta, practitioners usually do not care about that 0.1% in most cases, and they're sufficient with selecting the second best model. And if we can save the budget with this, it's actually beneficial for the model selector. Lastly, we switch to robustness analysis. So we compute the 95th percentile of the accuracy gap to assess the robustness. So, and we evaluate this for identification probabilities of 70, 80, and 90, as well as 100%. So what you can see from this table, what I would like to highlight is that model selector has a significantly smaller accuracy gap compared to the baseline methods. And that goes up to 9.8 times. So what this shows is that model selector is more robust compared to baseline methods. So talking about selecting the epsilon value, here I want to show you that selecting the identification probability when you use noisy labels will be as if you chose the best epsilon, but with the oracle labels. Now, what you can see if you take a closer look is that the trend stays the same. Even though that the curve changes, you can notice that if, for example, with noisy labels, epsilon with 0.35 was better, then also with oracle labels, epsilon with 0.35 will be better. What we also see from all of these experiments is that model selector is robust to epsilon selection. Even though you do not select the best possible epsilon, you do not perform a lot of grid search, you can still expect good results. And this selection is efficient compared to running time of baselines. So the total overclock time when we actually perform this grid search and then run model selector with the chosen epsilon is still faster than a single run of the baseline methods. From a practical guideline, if the practitioners don't want to perform the grid search, they can use the heuristic range of 0.45 to 0.49 for scenarios with high model disagreement. They can choose something closer to 0.49. And that will encourage more exploration and will behave more as random exploration. Across all of the experiments, we've seen that in this range, model selector mostly performs the best. So the question that you may have now is like, okay, if you can select the best epsilon just with noisy labels, do I need actually oracle labels at all? Do I have to pay that cost for prompting the oracle? And how we evaluate this is that we calculate the accuracy on true labels minus the accuracy on noisy labels. And as you can see from the table, the best model accuracy gap is consistently larger than 0, which means that even though you can select the best epsilon using noisy labels, you cannot just use the noisy labels to identify the best model, because the model you'll be selecting will be a wrong model. For example, for the DRI dataset, if you use the noisy, the majority vote, the selected model will have the accuracy gap of 14% compared to the best model, which you, of course, do not want to happen. So to conclude, model selector delivers competitive performance across various settings by capturing the discrepancy between the candidate models and the true labels with just a single parameter epsilon. Additionally, it relies solely on hard predictions without requiring access to internal workings of the pre-trained models. For the details, you can check out the paper and the code here using the QR codes. Thank you for listening.